Definition of an invertible matrix. Welcome, everyone. Let us begin our lesson on the definition of an invertible matrix. To start, let's look at some familiar ground. In basic and basic algebra, you are already well acquainted with the concept of a multiplicative inverse. To illustrate this, consider the number 5. The multiplicative inverse of 5 is 1 over 5, because when you multiply these two together, their product is 1. In mathematics, we refer to this result, 1, as the multiplicative identity. However, as we transition into matrix algebra, we encounter a key difference. We cannot simply divide one matrix by another in the way we divide ordinary numbers. Because division is not a defined operation for matrices, we instead use the concept of an invertible matrix to achieve a similar mathematical result. Over the next few slides, we will explore the formal definition of this concept and see how it functions as the matrix equivalent of a reciprocal. Formal definition. Now that we have established the analogy between basic algebra and matrix algebra, let us move on to the formal definition of an invertible matrix. First, we define a square matrix of order M as being invertible if there exists another square matrix B of the same order M, such that when you multiply these two matrices together in any order, the result is the identity matrix I of order M. To express this mathematically, matrix A is invertible if there exists a matrix B such that A times B equals B times A, and both of these products are equal to the identity matrix I. Whenever this specific condition is satisfied, we refer to matrix B as the inverse of matrix A. To make our mathematical writing more efficient, we use a shorthand notation. Instead of calling it matrix B, the inverse of A is denoted as A inverse. Consequently, we can rewrite our defining equation using this notation. A times A inverse equals A inverse times A, which equals the identity matrix I. In the next slide, we will break this definition down into 3 essential components to ensure you understand exactly why these requirements are necessary. Breaking down the concept. Now that we have looked at the formal definition, let us break it down into 3 essential components to ensure we fully grasp the requirements of an invertible matrix. First, let us discuss the requirement of a square matrix. You will notice that this definition applies exclusively to square matrices, which are matrices where the number of rows is exactly equal to the number of columns. This is a critical point because if a matrix is not square, it is mathematically impossible for the product of A times B and the product of B times A to both result in the same identity matrix. Second, let us examine the role of the identity matrix. Denoted by the letter I in the world of matrix algebra, the identity matrix acts as the equivalent of the number 1 in basic arithmetic. It is a square matrix characterized by having ones along the main diagonal and zeros in all other positions. For example, a 2x2 identity matrix is a square matrix with ones at the top left and bottom right corners, and zeros in the remaining 2 slots. Finally, we must consider the commutative property. As you may already know, matrix multiplication is generally not commutative, which means that multiplying matrix A by matrix B typically yields a different result than multiplying matrix B by matrix A. However, for a matrix to be the inverse, it must satisfy a very specific condition in both directions. This means that both A times B and B times A must equal the identity matrix. Real-world analogy, the undo operation. Now that we have covered the formal definition and the technical requirements, let us put this into a more intuitive perspective to help you visualize what is actually happening. Think of an invertible matrix as a specific process, and its inverse as the undo button for that process. To illustrate this, imagine you have a secret message that you want to protect. You can use a matrix, which we will call matrix A, to encrypt the message. In this scenario, multiplying your data by matrix is the process of locking the information. Of course, if you want to retrieve the original message, you cannot use just any matrix. You need a specific key to decrypt it and reverse the encryption. In mathematical terms, that key is exactly what we have been discussing: the inverse matrix, denoted as a inverse. So, if you first apply the encryption using matrix A and then immediately apply the decryption using a inverse, you return the message to its original state. Mathematically, this return to the starting point is represented by the identity matrix I, which, as we mentioned in the previous slide, acts as the multiplicative identity. Now that we have a conceptual grasp of how this undo operation works, let us move on to a concrete numerical example to see this verification process in action. Illustrative example. Now that we have discussed the theoretical definition and the undo analogy, let us put this into \text practice $ with a concrete example. We will verify whether a given matrix, which we will call matrix B, is indeed the inverse of matrix A. First, let us look at the matrices we are working with. Matrix A is a 2x2 matrix with 2 and 1 in the first row and 1 and 1 in the second row. Matrix B is also a 2x2 matrix, containing 1 and -1 in the first row and -1 and 2 in the second row. To determine if B is the inverse of A, we must follow the formal definition we established earlier. Step 1 is to calculate the product of A and B. When we multiply matrix A by matrix B, we perform row-by-column multiplication. For the top left element, we take 2 times 1 plus 1 times -1, which gives us 1. For the top right element, we take 2 times -1 plus 1 times 2, which results in 0. Moving to the second row, the bottom left element is 1 times 1 plus 1 times -1, which is 0. Finally, the bottom right element is 1 times -1 plus 1 times 2, which equals 1. As you can see, the resulting matrix has 1s on the main diagonal and 0s elsewhere. This is exactly the identity matrix I that we discussed in the previous slides. However, as we noted in our breakdown of the concept, matrix multiplication is not generally commutative. Therefore, we cannot stop here. We must perform step 2, calculating the product of B and A to ensure the condition holds in both directions. Multiplying B by A, we calculate the top left element as 1 times 2 plus -1 times 1, which equals 1. The top right is 1 times 1 plus -1 times 1, which is 0. For the bottom left, we have -1 times 2 plus 2 times 1, resulting in 0. And the bottom right is -1 times 1 plus 2 times 1, which equals 1. Once again, we have arrived at the identity matrix I. In conclusion, since the product of A times B and the product of B times A both equal the identity matrix, we have satisfied the formal requirement. We can confidently state that matrix B is the inverse of matrix A, which we denote as B equals A inverse. Keep this process in mind, as we will now move on to the key takeaways and some common pitfalls to avoid when working with these matrices. Key takeaways. First, an invertible matrix, which is also known in mathematics as a non-singular matrix, is defined as a square matrix that possesses an inverse. To be more specific, the inverse, denoted as a inverse, is the unique matrix that, when multiplied by the original matrix A, yields the identity matrix I. As we demonstrated in our previous calculations, the fundamental condition that must be met is that a multiplied by A inverse and A inverse multiplied by A must both equal the identity matrix I. Finally, always keep in mind that only square matrices can be invertible. If the matrix is not square, the concept of an inverse does not apply. Now that we have walked through the formal definition and verified it with a practical example, let us summarize the key takeaways from this lesson. While these points provide a clear framework, it is easy to make a few conceptual errors, so let us move to the next slide to discuss some common mistakes to avoid. Common mistakes to avoid. First, a very common misconception is assuming that every square matrix is invertible. While we have focused on matrices that do have inverses, in reality, not every square matrix possesses one. If you encounter a square matrix that does not have an inverse, we call it a singular matrix. Second, let's address the notation. In basic algebra, a negative exponent usually denotes a reciprocal, but in matrix algebra, a inverse does not mean 1 over a. It is important to remember that we cannot divide by a matrix. Therefore, a inverse is simply a symbolic notation for the inverse matrix, not a numerical reciprocal. Finally, be careful when verifying whether a matrix is an inverse. Beginners often check only one side of the multiplication. For example, they might verify that a times b equals the identity matrix and stop there. While it is often true for square matrices that if one side works, the other will as well, the formal definition we established at the beginning of this lesson requires that both a times b and b times a must equal the identity matrix to be officially confirmed. Now that we have covered the formal definition and walked through a practical example, it is crucial to discuss some common pitfalls. To ensure you master this concept, let's look at a few mistakes that students frequently make.